All right, so we're going to go ahead and get started. Welcome back, everyone. This week, we're going to be talking about vectors and complex numbers, which should be a little bit of a relief. I know last week we had pretty different lab and homework content from what was in the lectures. This week, we're returning to quote unquote normal, where the lecture was on very similar content to what we'll be covering in this lab. Now, I know that this week's lecture also had quite a bit of content. I guess I'll get an idea for how everyone here is feeling pretty soon with our pre-meeting or pre-lab poll. But certainly we've introduced a lot of content this week. So in the lab, I'm going to try and take things slow, reintroduce a lot of concepts to make sure that we are all understanding things really well. And then we'll walk through some practice problems as usual, just to sort of practice all that we've learned. So a quick overview of the program for today. We're going to start off with some announcements, just one sort of quick course-related announcement. Then we're going to do our attendance quiz. So this is actually separate this time from the pre-lab student feedback. I'll explain why that is in just a few minutes. As before, we'll go over popular questions from last week, the lab content itself on vectors and complex numbers, and finally, we'll end off with the post-lab student feedback. Two other quick notes. First one I wanted to just sort of mention, because I haven't said this explicitly before, but these particular labs are recorded. You might have already noticed that. I believe there's 2 TAs whose labs are recorded frequently on a week-by-week basis. This lab is one of those. That doesn't actually mean a whole lot for people watching it, but what it does mean is that I will always be covering all of the content in this lab, including the optional content. I might sometimes go overtime to do that though. Just to be clear, for everyone watching this live, like you're only expected to stay here for the hour of time that is allotted. But if I don't have a chance to get through the optional content in that allotted time, then I will say that the lab is over. I'll try to be very clear about that you're allowed to leave. But I will continue and go a little bit over time to always finish the optional content just for the purposes of the recording. So for you here, if you have a little bit of extra time after the hour, you're always free to stay back and continue watching some of the optional content. So first up, a quick announcement, and you've probably heard this somewhere else before too, but we are starting up homework review sessions held every Friday. So these are with the intention to sort of help all of you out with the homework problems. It is a 1-hour session held Fridays from 4 till 5 p.m. Eastern, as you can see on the slide. And the idea is that you will review, ask questions, work through the weekly homework problems with an instructor there. So I think it's going to be, kind of similar to labs in a way, but much more focused on just doing the problems themselves. Zoom links will be posted on Discord in the #course announcements channel, and recordings will be made available if you cannot attend live. So if that interests you, make sure to note it down on your calendar and join on Fridays from 4 till 5 p.m. Eastern. Okay, so we're going to launch into the Canvas attendance quiz, which, like I said, is a little bit different this week. So go ahead, you can open up your browser, get logged onto Canvas. If you're in the correct lab, it should show up. The quiz will be lab number 2A, and the quiz password is 6079, as shown on the screen. For future reference, we have also added this quiz password in the bottom right of every slide. So even if you join a little bit late into the lab, it's no worries. On every slide, you'll be able to see this password to make sure that you fill out your attendance to get credit for attending the lab. You'll notice that the question is not the usual rate the content or rate your understanding of the content on a scale of 1 to 5. The question this week is going to ask you the decimal number 2 is represented in binary as what, and then give you these 4 options. To be very clear, this quiz is not graded, although you should be able to do this question, and I'll give you the answer in just a moment. But it does count for your lab attendance. So be sure to go ahead and fill this out. I'll give you just a couple of minutes to do that. And in the meantime, I will also turn on the chat so that you can message me if you have any concerns or issues with the Canvas poll. So again, I'll give maybe just 2 or 3 minutes this time for anybody to fill out the Canvas quiz. If you are still having any problems whatsoever with the quiz, please message the chat and I'll see if I can give you a quick answer. If not, I will redirect you elsewhere. Okay, so for those of you who are messaging me saying that you are still in the wrong lab section, please just go ahead and email student@qubitbyqubit.org. I have thrown that in the chat. So again, if you're still having problems, there's no form this week just because it seemed like there were significantly fewer problems. But if you're still enrolled in the wrong section, so if it says 2B or something else, your lab number should say 2A if you are in this Zoom call right now. So go ahead and send an email to student@qubitbyqubit.org. Same thing goes if you're not seeing the attendance quiz. Also, please email that. Let's see. What's the topic? The topic for this week's lab is vectors and complex numbers. So it's the same content as the lectures. Put in the access code and quiz password, but it just doesn't let me submit. I think, yeah, so for any of these technical problems on Canvas, please just go ahead and send an email to student@qubitbyqubit.org. What did we discuss in the beginning? Just a couple of announcements. This lab is going to be recorded. So you can go ahead and watch the recording afterward for any updates there. Okay, so I think I will move on. Before we do though, just to I guess, give the answer here, the decimal number 2 is represented in binary as 1, 0. So if you had trouble doing that conversion, you can either go back and watch the recording of the previous lab session or refresh yourself on the lecture content. All right, so now we're going to do the part where I ask you how well you understood last week's content on a scale of 1 to 5. So you should see a Zoom poll popping up on your computer any moment now. So please go ahead, fill that in. I think you know the drill by now. 1 means you totally don't understand everything. 5 means basically that you've seen all of this before. So this is just to give me some sense of how everyone is feeling going into this lab. And by the way, the reason we're doing this on Zoom again instead of Canvas is just so that I can see real-time feedback of how everyone is doing. Okay, so it looks like most people have cast their votes here. Generally speaking, I think it looks a little bit lower than previous weeks, which I think is completely understandable. Like I said, there was a lot of content this week. But don't worry, we're going to be reintroducing a lot of things, as I said before. So hopefully going through it a second time will help. Okay, so before we get into this week's content, we're going to spend a little bit of time discussing last week's content. Same as before, these are just sort of questions that seem to trip people up fairly often. So the first one was a question on, actually, both of the ones that trip people up were questions on converting from Cartesian to polar coordinates. So the problem says to convert the following points from Cartesian coordinates to polar coordinates. I am going to go ahead and throw some equations up on the screen here. If you remember from our last lab section, this was the formulas you're supposed to use for this particular conversion when you go from Cartesian to polar. So no worries there. I'm just going to go ahead and start using these formulas. So if we want to calculate r is equal to the square root of x squared plus y squared. So our square root of x, x is just -2 here, okay, plus y squared, y is 2. Okay, and then I'm going to go ahead, work these out. We get the square root of 4 plus 4, which of course is the square root of 8. So that's good, no problems there so far. Now we're going to move on to theta, which is the inverse tan of, here we have y is 2 divided by -2. So again, all I'm doing here is I'm taking these x, y values, plugging them into these formulas that we had from the previous lab section. And if you go ahead and plug this in, I already did the tan function on a calculator. You were allowed to use a calculator for this question. You get that the inverse tan of 2 over -2 is minus pi over 4. And so at this point, you know, all we said last week was you just plug in numbers and you make the formulas work, and then you're good to go. And you might have tried to plug in this answer and it might not have been correct. And there's one way that you can check this. I actually alluded to this in the previous lab, not super directly, but if we just take a step back for a second and forget about all the formulas, forget about all the conversions we did last time, let's just do a really simple plot of where this point should be. So we're told that the Cartesian coordinates are x is -2, y is 2. So I'm just going to say that this diagram over here, let's say that this circle has radius root 8. So our point is going to be somewhere on this circle. And it looks like it should be roughly here. Because again, we have an x value -2 and a y value of +2. Like I said before, we're just going to assume that this circle has a radius of root 8. So that's all looking good. Now, what's our value of theta? Well, it looks here like our value of theta should be somewhere between 90 degrees up here, which if you recall from our lesson on radians is pi over 2, and 180 degrees down here, which if you recall again is pi radians. And if you sort of look at the symmetry of this, you might notice that actually it's perfectly in between these two. And if you think about this for a sec, what's exactly halfway between pi half and pi? That's going to be 3/4 of pi. So we expect that our theta should be about 3/4 of pi. But clearly that's not the answer we got. Our theta was negative pi over 4, which would actually put us somewhere down here. So if you take a second to actually draw this out and look at the circle with radius root 8, you'll notice that this answer of tan inverse 2 over -2 doesn't really make sense for our value of theta. And indeed, that is not the correct answer for the value of theta. So what happened here is that this inverse tan function, when you plug it in on your calculator, it actually doesn't do exactly what we described here. It is only ever going to give you angles on the right-hand side of the y-axis. So it's never going to give you anything over here. Now, why it's designed this way is kind of beyond the scope of this course. But the thing to remember is that it kind of cuts the circle in half. And so if you ever have a question that asks you to convert to polar coordinates and your point is in this left half of the circle, you have to add pi to whatever answer you get from the tan inverse function. So as a reminder, pi is 180 degrees. And you might notice that the difference between our incorrect answer down here and our correct answer up here is exactly that 180 degree pi radians of difference. So the correct answer here would actually be minus pi over 4 plus pi, which is 3 pi over 4, as we sort of figured out before. So I hope that makes sense. I know it's not, like, it doesn't really make a lot of sense why the tan inverse function would do this. Like I said, it's one of those things that you just kind of have to learn and then remember. But again, the basic idea is tan inverse will only ever give you angles on the right-hand side of the circle. And so if you have anything in the left-hand side, or another way of saying that is just anything with a negative x coordinate, then you will have to add this sort of corrective factor of pi onto your answer afterward. Okay, next question that tripped people up. Very similar question. Again, asking to convert from Cartesian points to polar coordinates. Now for this one, again, I left the equations in the bottom left of the slide, and I'll just go ahead and start plugging them in. So r is the square root x squared plus y squared. Our x here is 0. We get 0 squared plus y is 1. And that's actually just going to be 1, right? 0 plus 1 is 1, square root of 1 is 1, and so our radius is 1. This point just so happens to be on the unit circle. And in fact, if we just go over to our circle here, let's pretend that this circle is now the unit circle. We can pretty easily draw where this point should be, right? We can tell that it has an x coordinate of 0, y coordinate of 1, so it should be right up here on our chart. And if we remember our lesson on radians, the angle theta here we would expect is 90 degrees, which is pi over 2 radians. Okay, no problem. Let's go ahead and calculate theta using the equation at the bottom left of the screen. Theta is the inverse tan of y is 1 divided by x is 0. And immediately your math senses should be tingling here. We're trying to divide by 0 inside this fraction. And if you plug that into your calculator, it might give you an error, it might give you a number, but whatever it gives you is probably nonsense, because when you divide by 0, pretty much everything goes wrong within math. So this isn't going to give us any answer at all, basically. And so the only way of solving this problem is to look at the unit circle, to do exactly what I did over here, draw where the point should be, and then just kind of think about what the angle here should be. So in this example, it's easy, it's just a 90-degree angle. And so you convert 90 degrees to radians and you get pi over 2. But for these kinds of problems, your calculator does not help, unfortunately. So both of the challenging questions, I guess, in last week's homework had to do with the inverse tan function. It is a bit of a strange function. Like I said before, it only ever gives you values in the right half of the plane. When you have anything that's on the y-axis, it doesn't give you an answer at all. And so in these cases, you just have to draw a picture with the circle, draw where your point should be, and use this graphic to sort of figure out what the angle theta should be. All right, so I believe that's it. So before I move on to the actual lab content, I'll turn on the chat here again. Does anybody have questions about last week's, the challenge problems from last week? Okay, so one person asks, how do you map decimals to radian pi notation? Right, good question. So if you plugged into your calculator, let's say one of the tan functions that did happen to work, I don't know what an example would be. Let's say you had tan of 2 over 1. This is going to give you some decimal answer, right? It'll be, I don't actually know what this is, but it'll be some decimal answer like that. And you'll notice that a lot of the times when we write angles in radians, that we write them in terms of pi, right? We always have something like pi over 4. In order to get that pi over 4 value, you just need to divide this by pi. And so the way to see that is if I have this value here and I multiply it by pi divided by pi, what I actually end up getting is 0.145 divided by pi times pi. And so you take whatever's in your calculator, you divide it by pi, and then that's sort of the coefficient. The access code for Canvas, right, yeah, good question. So I was saying this in the beginning, but if you did join late, the access code will always be listed in the bottom right of every slide in the show. Actually, someone just said that in the chat too. But yeah, you can always check it even if you arrive late. The password for, okay, so if you didn't do last week's quiz, it's actually not open anymore. So even if I gave you the password, you wouldn't be able to do it. If you did have any problems last week, please go ahead and email student at qubitbyqubit.org. I will paste that email again in the chat. And they should sort out any issues you have with Canvas. Okay, so let's move on to this week's content. We have two main categories, as I said before. We have vectors and complex numbers. So in vectors, we're going to talk about how to represent vectors, which is primarily tying them to the Cartesian coordinate plane, all things that we have seen before. Addition, multiplication, decomposition, we will talk about all of these operations in the world of vectors. Then we'll talk about some basic operation on complex numbers, including the representation, modulus, and conjugate, which are two scary terms that are actually, I hope you'll find after this lab, not something to be feared at all. Multiplication in Cartesian form, multiplication in polar form is our optional content. And then applying vectors and complex numbers to quantum computing, we're going to do a very light introduction to something called the block sphere, which to everybody asking, why are we learning all this stuff about trig and complex numbers for quantum computing? A lot of it comes down to the block sphere. So if you can wait until the optional content at the end, we're going to start answering some of those questions for you, though the block sphere is going to come back for sure in later lectures. And if you did join late, by the way, one thing I mentioned right at the beginning is that these lectures specifically are being recorded. And so I will always go through all of the content, including the optional stuff in this lecture, in this lab time. However, I might go overtime. So I'm still going to do my best to do the required stuff in the hour that we have. But then I will tell you, okay, required content is over, starting the optional content, and I might go overtime. At that point, you're totally welcome to leave. I'm just going through all the content to make sure it's there for the recording. All right, so before we move on to vectors, we actually want to talk a little bit about why we need vectors in the first place. So as we talked about in the very first lab, classical bits are what computers use to represent information. So a classical bit can be either a 0 or a 1. In a quantum computer, we have these things called qubits, which is literally just a shortened version of quantum bit. And these qubits can be in superpositions of 0 and 1, which we learned means that they can sort of be both 0 and 1 at the same time. Now, in lecture, you learned that we have this notation called kets that we normally use to sort of distinguish quantum objects from classical objects. So really, this would be more correct to say ket 0 and ket 1. And the reason we do this is to make sure that it's very clear that the 0 over here is not the same thing as the 0 over here. Even though they have the same number, adding the ket around it makes it a totally different object. And we'll start to see how these ket objects behave in today's lab. So by way of analogy, in mathematics in general, we have two types of numbers. We have scalars, which are just your everyday numbers. So I'll take v as some variable equals 2. Other examples of scalar numbers include 3, 1.2, pi, whatever, right? All the numbers you know so far basically are scalars. Now we're introducing a new type of number called a vector. And vectors are basically sort of like combinations of numbers, right? So we have multiple scalar numbers make up a vector. Now, vectors, you will see them written in different ways. One way is using this sort of arrow on top of the letter that indicates that it's a vector instead of a normal variable. Sometimes you'll see it as just a bolded letter. So here we have just a normal script of V. If you saw a bold V, that might indicate it's a vector. And then the third way that you can show it's a vector is using a ket. So that's the same symbol we saw on the previous slide. It's just another way to represent that something is a vector. And just like the previous slide again, the reason we use this notation in the first place is to emphasize that the scalar value v is not the same thing as the vector v arrow. So these are just some notational things. Let's go ahead and look at what vectors actually are in sort of a more geometric sense. So when we talk about vectors here, we write them in sort of this weird way where we have one on top of the other. But really all this is saying is that the x coordinate is 2 and the y coordinate is 1. So we might write a Cartesian point as just 2, 1, and you'll see that the vector is really just like you stack a coordinate point vertically instead of writing it horizontally. It's really not that different. So if we were to draw this on our coordinate plane, we would have an x value of 1, 2, and a y value of 1. We would end up at the point right here. And just as a convention, usually when we talk about vectors, we draw them as an arrow going from the origin to some point out on the plane. Vectors don't have to start at the origin. They could start, in theory, anywhere and go to any other point. But when we're talking about them here, they're almost always just going to be starting at the origin, with one exception coming in just a few slides. So as I said before, when you see a vector written as sort of two numbers stacked on top of each other, what that's really saying is the x coordinate is on top, the y coordinate is on the bottom. And in this sense, you've already seen tons of vectors in your education with mathematics, because every vector is really just a point on the Cartesian plane. It's an xy point. Now, these x and y values in vector language, I guess, are called components. So we would call 2 the x component of the vector and 1 the y component of the vector. So we talked in lecture about a few terms. Every vector has both a magnitude and a direction. This is actually sort of the defining property of a vector, is that a scalar will only have a magnitude, while a vector has both a magnitude and some direction that you're going. And we saw that the way to calculate these was with these two formulas, which can look a little bit scary. The first one here, we use this sort of double bars around the vector to indicate the magnitude, and it's computed using that formula. And then we use this sort of sideways angle looking thing to indicate the direction of the vector, and it's computed using our familiar inverse tan formula. So I'm going to bring back some of the equations we saw actually in the problems from last week, and you should notice that these look very, very similar to the equations we're giving you now. As you'll see in a few slides, there is a pretty solid connection between this sort of vector values up here and the polar coordinates that we learned about before. So just to do a quick example, if I were to calculate the magnitude and direction of this vector here, well, I'm just going to use my formulas. They're on this slide. So the magnitude of v is equal to, using this formula, square root of vx squared plus vy squared. So remember, we said that vx is always the top number, vy is always the bottom number. So this is going to be 2 squared plus 1 squared, which is just the square root of 5. And so what this means geometrically is that the length of this arrow from the origin to our point is square root of 5. Next up, let's calculate the direction of the vector. So that's again this angle symbol followed by our vector v. Using our formula, it's the inverse tan of vy over vx. So you need to sort of flip the order of these two. It's going to be 1 over 2 in our inverse tan. And if you work that out on your calculator, you'll get about 0.46. Again, what this means geometrically is that the angle from the x-axis to this arrow is about 0.46 radians. I will note here that the same sort of caveats that we had with inverse tan that we talked about at the beginning, where sometimes you can get divide by 0, sometimes it just gives you the wrong answer, they all still apply here. So when you're trying to compute the direction of a vector, you have to keep those same things in mind. All right, so now that we've seen a little bit about how vectors are represented, we're going to move on to vector addition. So before we try doing this problem, I am actually just going to throw a quick formula on the screen here. So in general, when you're adding two vectors a and b, the x coordinate, or sorry, the x component of your resulting vector should be the sum of the x components of your two addends. And same thing with the y. So I'm going to give maybe just 30 seconds or so here for everyone to give this a try on their own. I'm going to throw up a poll. So once you solve this question, you can go ahead and fill out your answer on the Zoom poll that should be on your screen. And I'll just use this to get a sense of how many people are on the right track with how to do vector addition. And by the way, I will go through this problem afterward. I just want to give everyone a chance to try it on their own first. Okay, so if you're still working, feel free to keep working on the problem. I'm going to go ahead here and show how I would do this. So to add these two vectors, we have 2, 1 plus 3, 3. Oops. And the definition of vector addition just tells us to essentially add the x components, which is those two on top. We get 2 plus 3. And then add the bottom components. We get 1 plus 3. Put that in a vector. And we get 5, 4. So that should be our answer here. If you want to look at what this looks like on the coordinate plane, I can show you that really quickly. So one of our vectors was 2, 1. So I'm going to go over 2, up 1, because again, the first coordinate is our x, second coordinate is our y. So that's where this first vector is. Our second vector was 3, 3. So I just have x value of 3, y value of 3 as well. That's my second vector. And then you'll notice that our answer was 5, 4. So x coordinate of 5, y coordinate of 4, it sits up there. That's our answer. Now, I would typically recommend doing this the algebraic way. So just writing out all these vectors, summing up the top row, sum up the bottom row, you get your answer. But if you are curious, there's a way to see this visually. You might notice that before I said vectors normally start at the origin, so here's where the one exception comes in. If I draw, starting from my 2, 1 vector, the vector that I'm adding on, this 3, 3, instead of starting at the origin, I'm going to start at the end of the 2, 1 vector. So starting from here, take my 3, 3, I go over 1, 2, 3, up 1, 2, 3, and you might notice that I end up at the answer. We can even do this the other way around. If I start at the tip of my 3, 3 vector, and then I go 2 to the right and 1 up, I also end up at the answer. So you can do this by sort of adding vectors, drawing arrows on a grid. I personally think it's easier to do it this way, but it really is up to you. Last topic we'll talk about with vectors is something called vector decomposition. Now, when I first learned this, I was kind of confused why it mattered at all. So if you are having the same feeling right now, I totally empathize with you. I promise this stuff will become important very soon, but yeah, we'll go over it here just to give you the idea. The basic idea is that any vector, so for example, this 3, 2 vector, it can be written as the sum of vectors with zeros as one of their entries. So in this case, it seems most sort of obvious or most easy to write it as 3, 0 plus 0, 2, remembering that if we were to do the vector addition here, we're just adding the top row to get 3, adding the bottom row to get 2. So what does this look like on the grid? Well, I've already drawn the 3, 2 vector here. So remember, we went over 3, up 2. And what I can do is I can do the graphical addition process that I showed you on the previous slide, where we go over by 3, that's the 3, 0 vector, and then up by 2, that's the 0, 2 vector. And we get to our 0.32. So if you get any questions on this homework or future homeworks that ask you to decompose a vector, all they're asking for is a sum of vectors where the entries are 0 in one of the two components. Hopefully that's clear. I'm not going to do another example of this, but we are going to get to the question slide, I believe. So if you do have any questions on vector decomposition or any of the other things that we have talked about so far, please go ahead and throw those in the chat right now, and I'll do my best to answer them. Right, so good question here on vector decomposition. Do both of the vectors need, I'm assuming that was 0, or only one of them needs 0? All of them need 0. So when you are doing a vector decomposition, the idea is to write it as a sum, so adding two vectors, where all of the vectors you're summing together have a 0 in at least in one of their components. When you add vectors, it is always just 2, or can you add more than 2 together? You can absolutely add more than 2 together. And so to do that, if I had 1, 2 plus 3, 4 plus 5, 6, what that equals, again, I'm just going to sum all of the numbers in the top row. And so we get 5 plus 3 is 8, plus 1 is 9. And then all the numbers in the bottom row. 6 plus 4 is 10, plus 2 is 12. And you can do that with more vectors as well. Last question, how could a 0 vector qualify as a vector if it has 0 magnitude? Yeah, good question. So sometimes you will hear this term used, the 0 vector. And when people talk about the 0 vector, they might write it as this, again, just to indicate that it's 0 vector instead of 0 the scalar. And that's just equal to the vector that has zeros in all of its entries. This does count as a vector. I don't know if I really have a good reason as to why that is. It's still a point on the plane. It just happens to be at the origin, so there's no real arrow to talk about. And you're absolutely correct in saying that the magnitude of this is 0, and the angle of the 0 vector, we say it's not well defined. It could technically be anything because, as you can see, there's no arrow that has an angle with the x-axis. I don't think we'll be quizzing you on the 0 vector. It's kind of just an edge case, so I wouldn't worry too much about it. Anyhow, we are going to charge on here and talk about the second topic for this lab, which is complex numbers. Now, you were already introduced to complex numbers in the lecture. You probably saw a slide that was very similar to this. So you know that these new things, I guess let me just do a quick recap. So in the beginning, we talked about scalars versus vectors. And these are both kind of types of numbers. And for some of you, vectors might be a new type of number. Complex numbers are yet another type of number. And they are very closely related, as we will see, to vectors. So all of the stuff we just talked about vectors, keep that in the back of your head because it's going to be very useful when we talk about complex numbers. So complex numbers have a real part, which is just a regular scalar like we know. And then they also have this imaginary part. And I think most mathematicians don't like the term imaginary because it makes it sound like it doesn't exist. Complex numbers are super important in physics. So they absolutely do exist, at least in some sense. And so that's why we're teaching you about them here. The imaginary component is made up of what we call the imaginary unit. So remember this little I, it's not a variable, it's actually a number, and it's defined as the square root of -1. The imaginary coefficient, that's just some other real number, a scalar like you're familiar with. So let's talk about how to represent complex numbers on the plane. Now you should notice this sequence of slides is going to look really similar to the vector sequence as well. So the basic idea to draw complex numbers on the plane is that instead of having, remember before we had an X and a Y axis, now we're going to call these things the real axis and the imaginary axis. And we can think about our complex number, even though we usually write it this way, we're going to think about it as a vector. It has, instead of an x component and a y component, it has a real component and an imaginary component. And so we can draw it on the coordinate space in the same way that we would draw a vector, by going sort of a steps across on the real axis and then b steps up on the imaginary axis. So let's do an example of that. Suppose we have the complex number 2 plus 3i, and you're asked to draw it on the plane. First thing you do is you convert it to a vector. You don't necessarily have to write this out, but you can just do it in your head. And remember, from vectors, the top is the x component, the bottom is the y component. The only difference here is that we have different names for them. We call it the real component and the imaginary component. When we draw them on the plane, though, it looks the exact same. We're going to take 2 steps over to the right, 3 steps up, draw an arrow, and that is where our complex number z is in the complex plane. So I kind of rushed through that, but hopefully you can see that the idea is very similar to drawing a vector on the plane. Like I said, complex numbers are very similar to vectors. So in the complex number world, we have these 2 new things called modulus and conjugate, and they have sort of a special notation. So the first one is called the modulus, and we denote it with a single set of bars around the complex number. You'll notice that this should look very familiar. Before, we taught you that there was a double bar thing for vectors that was the square root of vx squared plus vy squared. This, as you can see, is a very similar idea. The x component, remember, we can write this z complex number as a vector, ab. So again, we're just taking the top component squared plus the bottom component squared and square root it. It's actually the exact same formula as what we had for the vector magnitude. On top of that, as I said before, the vector magnitude was the same as the formula we had for radius in polar coordinates. So all of these ideas are connected. All of them have to do with vectors, complex numbers. It's all the same idea. This next one, conjugate, is not something we've seen before, but I promise that it is fairly straightforward. The conjugate of a complex number, we draw it with a little bar. So sometimes you'll even hear this called, instead of conjugate z, people will just say z bar. And the only difference is you flip the sign in between the real and imaginary components. So a plus ib becomes a minus ib. You don't need to know much more about that. For now, you really just need to know how to do these computations. So again, I'm going to throw up a poll for everybody here to give this a try on their own with a sample question. Here's the 2 formulas from the previous slide. So again, we have our modulus of a complex number and our conjugate of a complex number. And I'm going to ask you, everyone here, to compute the modulus and conjugate of the complex number 2 plus 3i. So you should see a poll here on your feedback, on your screen any moment. The poll is just going to ask you for the modulus, I believe, but yes, there's the poll. So try out finding the modulus and the conjugate for yourself, and then I will do this question for everyone in about 30 seconds. Okay, so as people are finishing up that question, I'm going to go through this and do it ourselves. I'll start with the conjugate, just so that if you're still working on the modulus, you can do that. So in our definition up here, we had z equals 2 plus 3i. I'm just going to remind ourselves what a and b are. So remember, in general, our complex number was a plus bi. And so here we have that our a equals 2 and our b equals 3, just by sort of matching those variables. And so our conjugate is just defined as a minus ib. So my a is 2 minus b is 3. So that would be our answer for the conjugate. Let's look at the modulus next. Actually, I'll end the poll here. Yeah, let's look at the modulus next. So again, by definition, we have that the modulus of a complex number is the square root of a squared plus b squared. So I'll just write that explicitly here. It's the square root of a squared plus b squared. I'm going to go ahead and plug in our values. It's the square root of a is 2 squared. B, we said, is 3. Working this out, we have the square root of 4 plus 9, which is root 13. So I don't remember which one that was on the poll, but the magnitude for this complex number should have been root 13. So let's talk a little bit about complex number addition. Now, I'm going to throw up a really scary looking formula, which is technically how you do complex number addition. But I promise it's not really all that complicated. It's really just what we saw before with guess vector addition. So in order to add two complex numbers, we're actually just going to take the real component of both those complex numbers, add them together, and that gives us the real component of our answer. Likewise, for the imaginary component, we take the imaginary component of the two things we're adding, add them together, and that becomes the imaginary component of our answer. This is quite similar to how you add vectors, where we added the x components and added the y components. And so if you have a question like this, z1 plus z2, you can literally just line up the columns. So I'm going to add the real parts of these numbers, 2 plus 3. We get 5. That's the real part of our answer. And then we'll take the imaginary parts. Add them up. You get 1. That's the imaginary part. And so just like in math, normally we can drop the 1 in front of the I. So you might see that written as just 5 plus I. So just to review, you take the real parts of the things you're adding, you add them together, and that gives you the real part of your answer. And then you take the imaginary parts of the things you're adding, add them together, and that gives you the imaginary part of your answer. Okay, complex number multiplication is a little bit more complicated, unfortunately. But as I will show you, it's not as complicated as it first looks. So just like before, here's a scary formula to start things off. Yes, that's a lot of letters. There's no sort of easy way to see what this AC minus BD business is. So instead, we're going to do this the long way. We're going to just work it out, and I'll show you how this is very similar to how you would multiply two polynomials. So I'm going to write my two numbers down here. We have Z1 times Z2. So I'm just going to fill in these definitions. Z1 is 2 plus 3i. Z2 is 3 minus 2i. So far, so good. Now, if you remember from polynomials, the way to evaluate this is to kind of look at the first thing here times both of the things in the other bracket. So I'm going to do that. 2 times 3 is just 6. 2 times minus 2i is minus 4i. And then for the second half, you look at the second number times each of the numbers in the other bracket. So here I have 3 times 3i is 9i. And then 3i times minus 2i, this is getting to be a lot, but our coefficient is minus 6. And then we have I squared, just like that. Okay, so we're going to collect like terms here. We have 6 minus 4i plus 9i is plus 5i. And our I squared, we can actually simplify that a bit. If you remember, I is defined as the square root of -1. So if we square both sides, we get that I squared is equal to -1. So here, we're going to have -6 times I squared. That's just -1. That actually turns into +6. And so our final answer is 12 plus 5i. So again, this is how we do complex number multiplication. You can actually just work out this formula for yourself. You could do exactly the same process I just did. I prefer to just do this process instead of trying to memorize this formula. Either one is fine. You can just memorize the formula if you'd like. But I would personally recommend just remembering how to expand and multiply polynomials. That's the best way to do this. Okay, so the last topic for today is on the polar form of complex numbers. So as I said before, complex numbers are very tightly related to vectors. As we saw, there was some new concepts. For example, multiplication. You don't really see multiplication of vectors, but we can multiply complex numbers. And just like vectors, remember, in vector land, we talked about Cartesian coordinates. We also talked about polar coordinates. Complex numbers, in a very similar way, have both a rectangular Cartesian kind of form and what we call a polar form. What we've looked at so far is the Cartesian form. So here I'm going to introduce the polar form. Now, this is going to start off with something called Euler's formula. Now, take a look at this for a second. We'll break it down. The E here is just a constant, just a regular number. It has a value of approximately 2.718, I believe. And this value goes on forever, just like pi. The I value up here and over here, that is our I equals square root -1. That's our imaginary unit. And then this phi variable that we see in here, you pronounce that as phi. This is just a variable. So you can plug in any number there and this equation will hold. So now that we've talked a little bit about what it means, let me just take a step back to say this is a really weird equation, right? Like on the one hand, on the left-hand side, we have an exponential with the imaginary unit in the exponent. And so, normally when we write something like e squared, that equals e times e multiplied by itself twice. What does it look like to multiply something by itself I times when I isn't even a real number? So that's weird. And then on the other side of this equation, we have the trig functions popping out of nowhere. So you can prove this mathematically, it's true, but it's certainly not obvious. And so I'm just going to kind of state it as a fact. Some people say this is one of the most beautiful equations in mathematics. We will be seeing it a lot in quantum computing. So just take a second to take this in, try to sort of remember what it looks like. We will be using it a lot in the future. Now, the first thing I want to point out that's interesting about this equation, let's just forget about the left-hand side for a moment and focus in on the right-hand side of this equation. Remember with complex numbers, this is really just a complex number here, right? Our cos phi is the real part, or A, and sine phi is the imaginary part, B. And remember that we said we could write complex numbers as vectors. So if I went and wrote this as a vector, we would have cos of phi as the real part and sine of phi as the imaginary part. And if you think back to when we talked about vectors, this is really the same as a coordinate point with x coordinate cos phi and y coordinate sine phi. This should look familiar. If you think back to our previous week, we said that the definitions of cos and sine were the x and y coordinates of a point on the unit circle. And so here we have a very close relation to the unit circle. Let me say that again. We had as our definitions of cos and sine last week that they are the x and y coordinates of a point on the unit circle. And so if we draw a unit circle on our complex plane, this cos phi plus I sine phi is a point somewhere on the unit circle The only difference now is, again, instead of the XY axis, we have the real imaginary axes. So it turns out that this little e to the I phi thing is just a shorter way of writing a point on the unit circle. So let's talk about how we write complex numbers in this form. If I have a complex number z that is x plus iy, we can go ahead and write it as some point on the unit circle, which is what this cos phi plus I sine phi is, times the magnitude. So remember, or sorry, I should say the modulus of z. So remember, a complex number can have a modulus that is greater than 1, but every point on our unit circle has a radius of 1. If I go ahead and just multiply this, so for example, say we have a point way up here that has a radius of 2 instead, I could just multiply everything, scale it up by 2, and we still have the same situation. So all we're saying here is that our complex number z can be written as a point on the unit circle blown up by some radius. And as we just saw with Euler's formula, this cos phi plus I sine phi business can be written as e to the I phi in short. And then we just name this modulus z as r, which is very suggestive of radius. Now, the way to sort of convert a complex number into this form is with these equations. So our vector radius is just the modulus of z. We've seen that equation before. And phi, this is actually, I should have written, equal to the angle of, z, if you thought of it as a vector, which is just the inverse tan of y over x. Putting all these things together, we have that a complex number z, while you can write it as x plus iy, you can also write it as r e to the I phi, which again, looks super weird, and it's not clear why this should be true, but Euler's formula tells us that it should be. So I am running a bit low on time here, but we're going to do just one last example to demonstrate how to convert from a regular complex number to the polar form of a complex number. And you'll notice that this process is very, very similar to converting from Cartesian to polar coordinates. So here is a sample problem, z equals 2 plus 3i. I'm going to throw the equation from the last slide just on the top right here. We also gave you these two equations for calculating the vector radius and angle phi. So those are the two variables that appear up here. And the question now is to calculate z in polar form. Now, the way you do this is you always start by just computing r using this formula. Then you compute phi using this formula. And then to finish things off, you just write it as r e to the I phi. And you can say, by some magic called Euler's formula, these two things are equal. So I'm going to give everybody about 60 seconds or so here to start working on that problem. And we have one more Zoom poll that's going to pop up on your screen asking for the angle phi for this particular problem. So try working out the radius, try working out what phi should be. And then I will go ahead and do this question for everyone here. I will go just a couple minutes over time, but like I said, this is the last question for the required content. So we will be done pretty shortly. I'll give just another 40 seconds or so for everybody to work on this problem on their own, and then I will show how to solve it. Okay, so as people are still working on that, I'm going to go ahead and start off calculating the radius of this complex number, or r. Now, using our formula here, we have that the radius is just the modulus of z You don't have to write this step, but I'm just trying to get you used to the notation that we've introduced. So the modulus of z is equal to the square root of the x coordinate plus the x coordinate squared, sorry, plus the y coordinate squared. And remember, in complex numbers, instead of x and y, sometimes we will call these real and imaginary. So here my real part x is 2, my imaginary part y is 3. So I'm going to take 2 squared plus 3 squared. And this is equal to the square root of just squaring these numbers, 4 plus 9, and then adding them together, we get 13. Now for the inverse tan, we again use our formula given up here. So phi is the inverse tan of y divided by x. So remember, y is imaginary, x is real. So I'm going to take the inverse tan of 3, or y, divided by 2. So that was the answer we were looking for in the poll. And if you work this out on your calculator, just as sort of a final step, you would get about 0.98. Last step here is to write it in so-called polar form. And this is literally just combining what we've seen. So polar form, remember, is r e to the I phi. We got that from our formula on the top right. And then we just plug in numbers. For r, we computed square root of 13. And then we have e to the I, phi is 0.98. And that would be our answer in polar form. This slide is just a quick summary, I guess, of the steps that I just walked you through. If you're asked to find the polar form of a complex number that looks like this, remember that this is really the same as asking for the polar coordinates of x comma y, where x is the real component, y is the imaginary component. How do you do that? First, you find the vector radius r by taking the square root of x squared plus y squared. Then you find the vector angle phi by taking the inverse tan of y over x. And again, this comes with the same caveat as we talked about at the beginning of this lab, where you sometimes have to be careful when using inverse tan. And then the last step is the easiest. You just combine them using this r e to the I phi formula to get your final answer. So hopefully that slide is helpful as you're going through the homework problems. I am going to pause here for any questions that you might have about complex numbers and polar representation. I know that all this business with Euler's formula is really, really weird. I agree. It's just one of those things that you will learn to live with in quantum computing. One person asks, isn't the modulus just the magnitude? Yes, absolutely. So we sort of have 3 different names for the same thing. So we have r as the radius being defined as square root of x squared plus y squared. And remember, this came from polar coordinates, right? Then we had the magnitude of a vector being defined as the x squared plus vy squared. That was from vectors. And then finally, we have the modulus of a complex number is the square root of a squared plus b squared, the real and the imaginary part, which we got from complex numbers. So these 3 things, you're totally correct to point out that they are heavily, heavily related. And so you're free to think about them interchangeably. There's not really any difference. I think the main takeaway is just that coordinates, vectors, and complex numbers are all really the same thing at some level. And so they do have very similar math behind them. Okay, so could you go back to the previous, oh yeah, I'll go back to the previous slide with the example. Here we go. So I'll just leave that there for a few more seconds. Does the modulus have any relationship with absolute value? Good question. The short answer is yes. That's why it's drawn the same way as the absolute value. The exact reason why I won't go into. I think it's best for quantum computing to just remember the definition as we've given it here. If you are still having trouble with this kind of thing, I would highly recommend looking into complex numbers on something like Khan Academy, maybe. I think that's a pretty good resource. Or, of course, going back and watching the lectures and labs again. I think a lot of times just hearing the content again can be a good way of sort of resolving some doubts. So just so you know, I guess if you want to Google other resources, all of this would fall under complex numbers, or if you are specifically having troubles with the latter part of the lab, the polar form of complex numbers. Okay, so my apologies for going a few minutes over time here. I'm going to throw up the post-lab feedback poll. So same question as at the beginning. On a scale of 1 to 5, how comfortable do you feel with this week's material? So as I said, hopefully I've cleared some things up. If not, I would highly recommend going back and watching the lab again. As I said, this is recorded. It'll be posted on Discord soon. So if you do have any questions or doubts, feel free to go back and watch the relevant part of the lab, especially as you're going through your homework. Okay, so that brings us to the end of our lab for this week. So I guess, yeah, if you do have to go now, feel free to head off. That's all the required content. You should be good to do all of the homework now. The optional content that's coming up, I just realized there's a typo, content. The optional content coming up is going to be a little bit more on polar complex numbers, specifically how you multiply polar complex numbers, and then a brief introduction to the block sphere. So I estimate that'll take maybe another 15 minutes or so, but as I said, there is no obligation at all to stay for that time. If you have to head out now, no hard feelings. I hope you have a good week. Good luck with the homework, and we'll see you again next week. For all of you who are able to stay, I'm going to just take a quick 60-second break, and then we will launch into the optional content momentarily. Okay, so let's get started with this week's optional content. The first piece of optional content is highly related to what we just talked about with the polar form of complex numbers. So remember, with the polar form of complex numbers, it's very, very related to this formula called Euler's formula. I actually didn't put it on this slide, but just to write it again for you, it's e to the I phi equals cos phi plus I sine phi. And what we noticed is that this cos phi plus I sine phi piece, if you write this complex number as a vector, it looks very similar to the definition of sine and cos that related to the unit circle. And so what we said is this e to the I phi thing is just a fancy way of writing a point on the unit circle. The only difference being it's not in the xy plane. Now it's in the real imaginary plane, or the complex plane. So it turns out that one of the uses for polar form, one of the reasons we would care about polar form at all, is because it makes multiplication of complex numbers a lot easier. If you remember from the slides before, multiplication of complex numbers had this really complicated formula at the top of the slide. It required us to multiply out sort of these two expressions in brackets. We had to know what I squared was. We had to do a bunch of additional math. And sometimes that stuff can be really, really tedious. Polar form offers us an alternative that you'll see is a lot faster and a lot easier. Now, before we introduce how to do that, I'm going to do this problem in sort of the way that you might do it before I teach you how to multiply in the polar form. And the way to do that is to first convert these two numbers back to the Cartesian form of complex numbers, so something that looks like a plus bi. and then multiply them together using the same strategy we had before, where we sort of multiply all 4 combinations of numbers. We remember that I squared equals -1. We work everything out and we come up with an answer. So this is going to take a little while, not too long, but I'm just going to kind of work through the math. We've seen all of this before, so it shouldn't be anything too new. So to convert this back to Cartesian form, I'm going to use our Euler's formula that we mentioned before. So this e to the I pi over 4 is really just equal to cos of pi over 4 plus I sine of pi over 4. And then we know that cos and sine of pi over 4, we can figure out what those are either with our calculator or by using the unit circle. They're both going to be √2/2. And so our final answer is √2/2 plus I times √2/2. Now let's do the same thing again. Here we get, this time there's a 2 multiplying everything. So cos pi over 4 plus I sine pi over 4, which, as we said, just don't forget there's a 2 this time. √2/2 plus I √2/2. Then if I multiply out the 2, we get that this is just √2 plus I times √2. So again, to do those conversions, I just used Euler's formula. Then I'm going to multiply these things together. So our Z1 is √2/2 plus I times √2/2. And then our Z2 is just √2 plus I √2. Now, recall how we did this before. We had to just start off by multiplying this term by each of those terms. And so the first number is √2/2 times √2. Now, remember, if you have the square root of 2 times the square root of 2, that's just going to be 2. And so our first term here is 2/2. Multiply these two together and we get I times 2/2. Now we'll skip to the second term. We'll multiply these ones like that. And we get another I 2/2, remembering again that √2 times √2 is just 2. And then our final term is I squared times 2/2. Now we can simplify this a bit and collect like terms. So this is just 1. Here we have 2I. Here we just have 1I squared. Remember that I squared is -1. So we have a -1 there. And the 1's cancel out, so we actually just get 2I as our answer here. So before I go on, I'll just say that this is a perfectly valid way of doing multiplication of numbers in the polar form. If this makes more sense to you, you're welcome to use it, but there is a much easier way. So I'm just going to clear the slide, fresh problem again. One of the big benefits of Euler's formula, we haven't really talked about this much, but the exponential that it allows us to write, this e to the I phi, because it is an exponent, it obeys all of the exponent rules that you might have learned in school. So these are things like, if you have x to the a times x to the b, you get x to the a plus b. If you have x to the a over x to the b, you get x to the a minus b. So hopefully these relationships look familiar. I believe actually there were some questions like this on one of the homeworks from before. So the nice way of writing this, the nice outcome, I guess, of writing this as an exponent instead of cos phi plus I sine phi is that you can use these rules. So if I just write my Z1 and Z2 down here, my Z1 is 1 times e to the I pi over 4. My Z2 is 2 e to the I pi over 4. Now I'll multiply these together. My 1 times 2 is just 2. And then I have e to the I pi over 4 times e to the I pi over 4. And now we can use our first exponent rule right there to write this as e to the I pi over 4 plus I pi over 4. So again, because we had the multiplication of two exponents, we can use an exponent rule to sum the exponents, and they're going to be equal. Now, if I just add these two things together, yes, they are imaginary numbers, but we know how to add imaginary numbers. And we're going to get 2e to the I pi over 2, because a quarter plus a quarter is just a half. And it turns out that this e to the I pi over 2, if you use Euler's formula to convert this back to Cartesian form, it's actually just I. So our final answer here is 2i, which is the same as we got on the previous slide, luckily. Now, one way to sort of see this, I guess, on a coordinate plane, because remember, complex numbers are just vectors, we can go ahead and draw these two numbers on the coordinate plane. So Z1 has a radius of 1 and an angle of pi over 4. So it's going to be, radius of 1 means that it's somewhere here on this unit circle. And then angle of pi over 4, remember, is a 1/8 turn around the circle. So it's a little bit small here, but hopefully you can see that this is our Z1. Now for our Z2, it has a radius of 2, so it's going to sit somewhere on this circle. And it makes the same angle with the x-axis. Sorry, I should have written that this is pi over 4 as the angle. Z2 makes the same angle, but now it goes out to the radius 2. So it's a little bit messy, but there you can see our two complex numbers. And then the answer we get at the end is 2i. So remember, that's just going to be 2 along the imaginary axis, right up there. So one way that you can sort of see the multiplication of complex numbers in polar form is you start at one of them. So let's say that I start at Z1, then kind of the same idea as vector addition, where you sort of start at the tip of one and then add something else onto it. I'm starting at the tip of Z1, and now I'm going to rotate the angle of Z2 around this unit circle. So I would go another pi over 4 radians to get myself here, and then scale the whole thing up by the radius of Z2, which here is just 2. And that gets me to the final answer. So don't worry if you don't fully see this right now, but it's important to point out, because you'll notice in quantum mechanics and in quantum computing specifically, these e to the I pi over 4, e to the I phi operators, people talk about them as rotations a lot of the time. And that can be really confusing to students, because it's like, why does this e to the I phi thing have anything to do with rotations? The reason is because when you multiply by it, what you're really doing is you're rotating your complex number another, phi radians around the unit circle. So again, no worries if you don't see this right now, but it is a useful concept in quantum computing, and as we use it in the future, I'm sure that it will become easier to understand. So last topic that we're going to cover today is a very brief introduction to the block sphere. Now I'm going to start that off with a question. And the question is, how would you tell me where your hometown is? So this course has people from all over the world taking it. And let's say that, I can't just type in your hometown in Google or whatever, and you have to tell me a location of where your home is. So one way that humans have developed is these things called longitude and latitude. So for me, I would tell you that my latitude is, somewhere around here, right? And that narrows things down. That tells us that I'm somewhere on this line around the sphere. And then I would tell you my longitude. This is not actually where I am, but say it could be somewhere here. And once I tell you these two numbers, you know that I am located at where they intersect. So normally you'll see people write this as something like, oh, I'm 45 degrees latitude and 60 degrees longitude or something. Doesn't matter what the actual definitions are. But the basic idea is that they're using two angles to tell you a point on the sphere. The first angle tells you how far down you go, and the second angle tells you how far across you go. So hopefully this sort of sounds familiar if you're familiar with latitude and longitude. It turns out that we use a very similar system in quantum computing. So we have this thing called the Bloch sphere in quantum computing. We have a drawing of it right here. And we use two angles, same as latitude and longitude, except now we're going to call them theta and phi. And in the same way as longitude and latitude, if I tell you the angle theta, that is going to restrict my location to somewhere on this circle on the sphere. And once I tell you my longitude, or phi, then you know that I'm somewhere along this line on the sphere. And my actual location is where those two things intersect. So very similar idea. We're using 2 points to describe a location on the sphere. Now, I have another sort of question. Actually, before we do a question, let's do a quick example or two, just to show how this works. So for example, this point right at the top here, right up top on the z-axis, this would be the point you get when you let theta collapse all the way to 0. And in this case, the angle of phi actually doesn't matter. So whenever we have theta equals 0, you are at the very top of the sphere. Let's say we had a theta value of pi over 4 and a phi value of pi over 4. Where would this be? Well, you can start off by taking theta and going pi over 4, which remember is a, pi over 4. It should be pi over 2. That's what I wanted to say here. It's my bad, I just made a quick typo. Let's say both of those are pi over 2. Pi over 2 we know is just a quarter rotation. So my theta would go a quarter rotation down to here. And then my phi, or I should say quarter rotation down to here. And then my phi goes another quarter rotation all the way around to this point. And so this point right here is theta equals pi over 2, phi equals pi over 2. If we had something like theta equals pi over 2 again, but now phi equals 0, then we would simply have theta going down a quarter rotation, and then phi takes us nowhere. So in fact, this point right here is theta equals 0, theta equals pi over 2, phi equals 0. So hopefully that sort of makes sense how we label things on the sphere. I'm going to ask a question now, which is what restrictions should we put on theta and phi so that we can actually label every single point on the sphere? So again, I'll repeat that question. Sort of what limits, if I wrote, theta has to be greater than something, has to be less than something else, what limits would you place on these two numbers to ensure every point on the sphere is uniquely labeled? So think about that for a second. And there's actually a number of different ways of doing this, but the way that we sort of choose in quantum computing is, I'll just erase this. The way that we choose in quantum computing are these two restrictions. Theta has to be greater than 0, less than pi. Phi has to be greater than 0, less than 2 pi. So phi sort of has a twice as large range. And the reason for this, I'll just explain it briefly, though it's not a big deal if you don't fully understand this. Suppose that instead of pi, we let theta go all the way up to 2 pi. Well then, let's say that we had a theta value greater than pi. So pi would bring us a full half rotation around the circle, and then we would keep going up the back side of the sphere somewhere. So say we had a point down there. Then we could sort of bring this is hard to draw, but this is supposed to be pointing sort of backwards into a point in the sphere. Then our phi value would go all the way around to wherever that point lies on the sphere. This is totally valid, but you might see that another way of representing this same point is to just let theta go all the way down here. So still keeping it within a half rotation, and then rotating phi all the way around to the new point. It's hard to draw it on this screen, and so again, I apologize if it's not very clear. But suffice it to say that all of the values on the sphere can be captured with theta and phi in this range. Oops. So, final slide here is about the Bloch sphere. Now, the Bloch sphere is basically a way of visualizing quantum states. So quantum states are things like sort of 0, 1, superpositions of 0 and 1, other states, all these kinds of things can be visualized on the Bloch sphere. And the way we do that is by using the angles theta and phi that we talked about before. So when we label the Bloch sphere, the top point up here is labeled as the 1, 0 point. The bottom point down here is labeled as the 0, 1 point. And if you make these labelings, any point on the sphere is given by these two equations. I'm not going to go into too much detail here, primarily because you can just plug in certain values of theta and phi, and you will get these answers. So just as an exercise for yourself, remember that this point up here was theta equals 0, phi didn't matter. Just for your own practice, you can go ahead and plug this theta and phi into this equation, and you should get 1, 0. Likewise, we said that this point over here was theta equals pi over 2. I made a typo before, and phi equals pi over 2. So you can go ahead and plug that into this equation. You'll get something that has imaginary numbers. That's okay. Quantum states can have imaginary numbers. And so the basic idea is any point on the sphere can sort of be written as a vector. And this will help us a lot in quantum computing coming up very soon. So this was a very, very fast introduction to the Bloch sphere. Don't worry if you don't follow all of this. It will be explained in a future lecture with a lot more sort of visual aid. But just to give you an idea, this is where we're going. This is kind of like the end goal for all of this business with trig functions, Euler's formula, complex numbers. All of these things are converging on the Bloch sphere. We're going to get to it very soon, but this is just a little bit of a sneak peek. That brings us to the end of the optional content for this week. I will open up for questions again, although like I said, please don't worry if a lot of the extra content didn't make perfect sense. All that you need to do the homework is the required content, and all of the optional content that is relevant to quantum computing will be covered again in the future. So if you do have any questions, feel free to throw those in the chat, and I'll do my best to answer them. Okay, looks like no one has any. Oh, somebody does have a question. Okay, what's the third dimension in the Bloch sphere? Good question. So the third dimension in the Bloch sphere, you can kind of think of, I mean, when we draw it visually, it's just 3 x, y, z directions, right? But you'll notice that our vectors here only have 2 entries. So this can be a little bit confusing. And frankly, the Bloch sphere was very confusing to me when I first learned it as well. But the way that I would think of the third dimension, it's kind of like adding an imaginary number to one of the entries in your vector. So if we look at this formula over here, notice that the top number is never going to be a complex number. There's no imaginary I, there's no Euler's formula, it's just a cosine. The second one here, though, is a complex number, right? It has both a real part and an imaginary part given by Euler's formula. And so roughly speaking, you can think of this third dimension as being the imaginary dimension of this second component. It's not a perfect description, but that's how I would think about it. Why is it named Bloch? Bloch was either a mathematician or a physicist. I'm not sure which one, but he was someone who came up with this sort of representation to visualize quantum states. All right, so with that, I think actually, sorry, one more question, I'll answer this and then we will finish up here. By the way, thank you to everyone for sticking around. I know this has been a very long lab session, but again, it's all recorded, so you can go back and watch it again if you'd like to. And there was a lot of content this week, to be fair. So someone asks, from the Bloch sphere, the phi angle determines the rotation from the x-axis. So I'll go back here. The phi angle determines the rotation from the x-axis. That's why when it's pi over 2, it's on the edge of the sphere in the diagram. It's a little confusing to see it on the diagram. Yes, exactly. So phi measures the angle. So if we looked at this, I don't know if this will help. This might make it more confusing, hopefully not. If instead of trying to draw this in 3 dimensions, let's just look at it from the top. Let's imagine, sitting right on top of the sphere looking down, you would see the XY plane just like this. The angle phi is just the angle from the x-axis, like you pointed out. And it's the same sort of rules and conventions that we had for before. So it starts from the positive x-axis and it goes to wherever your line is. And because it ranges from 0 to 2 pi, it can be anywhere around the circle in the XY plane. All right, so hopefully that helps clear things up. Thank you all for sticking around. We will close off this lab now, but good luck with the homework. Definitely feel free to rewatch the recording if you have any questions, or as always, come on Piazza. A bunch of us TAs are very active there. Have a great week. Good luck on the homework, and I will see you again in 7 days.